Selecting and installing a solid wireless system for industrial applications requires special knowledge. But what do you need to know when selecting and setting up a wireless communication network? How do you know what type of antenna you should use and where you should mount it? In this video, we'll give you the information to answer these questions. We'll go over the different types of antennas, how they work, and how they're used, as well as some essential considerations when installing a wireless system. So let's talk about radio antennas. We all know what they are, but what is it that makes one type of antenna different from another? We'll begin by noting that all antennas can be divided into two general types: omni and directional. Omni antennas send and receive radio signals uniformly in all directions on a horizontal plane. Directional antennas, as the name suggests, focus their sending and receiving power into a comparatively narrow beam. Omni antennas distribute their radio energy in more of a donut shape and are well suited to situations where the antenna must send and receive signals from multiple directions. However, they don't have the straight line range of the directional antennas. Directional antennas can send and receive signals from significantly greater ranges than omni types, but are constrained to communicating only within the path of their beam. There are many different kinds of antennas, designed for a variety of applications and circumstances, but all types are categorized by three important electrical characteristics: antenna pattern, antenna gain, and antenna polarity. Let's explain what each of these characteristics are. Information between two wireless devices is transferred via electromagnetic energy, radiated by one antenna and received by another. The radiated power of most antennas is not uniform in all directions and has varying intensities. The radiated power in various directions is called the pattern of the antenna. Each antenna should be mounted so that its direction of strongest radiation intensity points toward the other antenna or antennas with which it will exchange signals. An antenna with nearly equal pattern intensity in all directions is omnidirectional. In two dimensions, an omnidirectional pattern appears as a circle. An antenna is considered omnidirectional if one of its two patterns, either azimuth or elevation, is omnidirectional. Beam width is an angular measurement of how strongly the power is concentrated in a particular direction. It can be broken into two-dimensional slices just like the antenna pattern. The beam width of an omnidirectional pattern is 360 degrees since the power is equal in all directions. Antenna gain is a measure of how strongly an antenna radiates in its direction of maximum radiation intensity, compared to how strong the radiation should be if the same power were distributed equally in all directions. An antenna's gain is used to describe the distance to the furthest point on the pattern from the origin. For an omnidirectional pattern, the gain is 1, or equivalently 0 decibels. The higher the antenna gain, the narrower the beam width, and vice versa. The amount of power that is received by the receiving antenna is proportional to transmitter power and antenna gain. Antenna gain and transmit power can therefore be traded off. Antenna polarity refers to the direction that the electromagnetic field lines point as the energy radiates away from the antenna. In general, antenna polarization is elliptical, meaning that the polarization of the radio waves vary over time. The simplest and most common form of this elliptical polarization is simply a straight line, or linear polarization. This is where the radio waves oscillate in only one direction. The direction can be either vertical or horizontal polarization. Of the transmitted power that reaches a receiving antenna, only the portion that has the same polarization as the receiving antenna polarization is actually received. Another important parameter for an antenna is matching impedance. For a radio to deliver power to an antenna, the impedance of the radio and transmission line must match the impedance of the antenna. Voltage standing wave ratio, or VSWR, represents the degree with which an antenna is matched to the radio system impedance. Most modern antennas, receivers, and transmitters are designed for peak performance when operating into a 50 ohm transmission line. The typical commercial standard for maximum allowable VSWR across the entire bandwidth of a system is 1.5 to 1. A VSWR of 2 to 1 or greater is usually considered unacceptable since it increases losses in the transmission line. This means that the antenna impedance must be in the range of 50 ohm. You should specify the maximum VSWR and the operating frequency bandwidth when specifying your antenna. Now that we've discussed the characteristics that define how an antenna operates, let's look at some of the most common antennas in use with industrial wireless devices today. The most common omni antennas are whip antennas, both the straight and articulating variety. They do not require a ground plane and are typically connected directly to the radio enclosure. This type works well with belt-mounted remote radios or other applications where mobility is a factor. This type does not radiate well out the top of the antenna and thus must remain vertical. Another popular omni antenna is the collinear array antenna. This is typically composed of several linear antennas, like the whip, stacked on top of each other. The more stacked elements within the collinear array, the longer the antenna and the more gain it has. When mounted, the antenna is oriented straight up and down, with the feed line at the bottom. This type is among the most powerful omnidirectional antenna, and so is well suited to situations where the location must send and receive signals from multiple directions. The most common directional antennas include Yagi, parabolic reflector, and panel antennas. A Yagi antenna is composed of an array of linear elements parallel to one another and attached perpendicular to and along the length of a metal boom. This causes the antenna to radiate energy in a beam out the end of the boom. The actual pattern depends on the overall geometry, including the number of elements, element spacing, element length, and so on, but generally is proportional to the length. So although it may look like an omni antenna, it does not function like one. A parabolic reflector antenna consists of a parabolic-shaped dish and a feed antenna located in front of the dish. Power radiates from the feed antenna toward the reflector. The reflector concentrates the radiation into a narrow pattern, producing a high-gain beam pointed away from the concave side of the dish. As a result, the parabolic reflector has some of the greatest range of any antenna type. The gain varies with the size of the reflector and the antenna construction, and antenna polarity depends on the feed antenna polarization. Panel antennas, also known as patch antennas, are another common type of directional antenna. They're typically thin and rectangular in shape, consisting of a sheet of metal mounted over a larger sheet of metal called the ground plane. These two sheets together form a resonant piece of microstrip transmission line. The low profile and weather resistance of the panel antennas make them well suited to indoor or outdoor applications. While transmitting in the direction the panel is facing, panel antennas are typically not as focused as Yagi or parabolic types, which have a narrower beam. This means that while it can cover a larger area, it will have less gain and range. Finally, we'll take a look at multiple input, multiple output, or MIMO antennas. These are actually an array of antennas, transmitting and receiving multiple data signals on the same radio channel at the same time. MIMO technology takes advantage of a natural radio wave phenomenon called multipath. With multipath, transmitted information bounces off walls, ceilings, and other objects, reaching the receiving antennas multiple times via different angles and at slightly different times. In the past, multipath signals caused interference and was considered detrimental to receiving the actual transmission. MIMO-enabled antennas can now take advantage of multipath behavior by using multiple antennas to greatly increase communication performance. All wireless products with 802.11n support MIMO, which is part of the technology that allows 802.11n to reach much higher speeds than products prior to the 802.11n spec. Now that we've examined the different types of antennas and their characteristics, we can look at some other considerations when mounting an antenna. The first thing you must consider is that antennas cover certain frequencies differently, depending on their size, type, and construction. The antenna you use must be tuned to the frequency of your application. As mentioned before, antennas need to have the same polarity, either horizontal or vertical, to send and receive data efficiently. For us, it's typically vertical. An omni antenna pointing straight up and down is polarized vertically. The directional antennas have markings on them indicating the vertical pole or V-pole with an arrow. To match the omni antenna, these must be mounted with the arrow pointing up or down. Mounting it left or right will weaken the signal. The next crucial consideration would be keeping other electrical objects away, having clear line of sight, and having proper antenna direction. Not only is the relationship between the antenna and the earth improved by mounting an antenna higher, resulting in better ranges, but the probability of interrupting the line of sight is reduced. You should avoid mounting next to solid objects such as walls, buildings, towers, or girders. The resulting reflected radio energy causes drastically reduced efficiency. A minimum of 6 feet is a good general rule to avoid excessive reflection. When considering the signal path, keep in mind that obstructions that block the path can greatly deflate the radio carrier wave because of the frequency range used in operation. Try to minimize obstructions such as trees, buildings, hills, and so forth. The allowed power output from the antenna varies by country and spectrum. For most industrial applications, the best way to ensure constant, solid communications is to make sure you have clear line of sight between your antennas. For longer distance outdoor applications, where the locations cannot be seen, software can be used for a path study, or you can request a site survey from ProSoft. Not only do you want to stay away from sources of electrical noise, such as power lines, electrical motors, solenoids, high power radio sources, or any high voltage power usage in order to improve signal reception, but you want to avoid the possibility of electrical shock, which can be fatal. Speaking of which, another important consideration when installing an antenna outdoors is to have proper lightning protection. Placing an antenna high above the surrounding terrain may give you great signal coverage, but it also makes it vulnerable to lightning strikes. Using a coaxial lightning arrestor with a grounding wire for each antenna can protect your radio equipment from serious damage. The grounding wire must be of the proper gauge as per the manufacturer's recommendation, and it must actually run to ground. Installing antennas can be a hazardous affair, so be sure to follow all safety warnings on your antennas and other radio equipment. When selecting your antennas and other components, once you've considered all the previous information, you'll need to determine required gain, determine the gain loss due to cabling, and calculate your total gain. ProSoft Wireless Designer software is a free tool to help you through this process and can be found on our website at www.prosoft-technology.com.